this. Yep, thanks for mine. All right. It's got shorter. It's people on camera. But thanks very much for the chance to talk. So I just wanted to talk about a topic that's probably a bit different to the other topics, but still involves waves, and hopefully this is work in progress. So hopefully some questions and comments really help going forward on this topic. So it's a collection of people at UWA. Engineers and also sports scientists. So,
oh, my computer's having a heart attack.
Okay. So, what's the motivation for this work? Well, there's a motivation from the point of sports. So, this is the open water swimming world championships, 25 kilometres. And you can see that this doesn't happen in sort of still water conditions. There's definitely surface waves present. So from the perspective of this particular sport, understanding how surface waves influences swimming performance is important. Most research to date on swimming has been done in swimming pools with flat water. So there's relatively little known or published in the literature about the influence of waves on swimming performance and behaviour. Maybe more importantly for the wider community is that open water swimming is a growing sport, especially in WA. Lots of people do it, and they do it over quite long distances, usually swimming to places like Rottnest Island here in WA, which is a 20-kilometre long swim. So understanding how waves may influence your technique and performance over that distance will, influence whether you enjoy it and come back and keep doing that exercise, which is important for your well-being, but also B, maybe help you get there and achieve your goal if you're swimming to a particular location. Maybe the third motivation for this work was that about 2 years ago, we refurbished a wave flume at UWA that is 54 metres long, 1.5 metres wide, and we can fill it up to a maximum depth of just over 1 metre, 1.1 metres. So you can imagine that's pretty much one lane of an Olympic-sized swimming pool. So we immediately thought when we were refurbishing it that this could be used for swimming research going forwards. There's a couple of sets of viewing windows, which I'll show you plenty of video looking through those a little bit later. There's 2 sets of those positioned along the flume. And the flume can do a range of different wave conditions. We actually have a paddle at either end, one for a piston paddle for sort of coastal applications and a hinge paddle for deeper water. And this is the piston paddle which we've used in this work. And the flume was refurbished for model scale testing. In fact, Hugh Wolgamott led the refurbishment of this flume, and we've done quite a lot of model testing in there. To allow us to put swimmers in there, we have to treat the water, and we use a chlorine and salt-free water treatment to do that. Okay, so I'll just go through some things. There's going to be plenty of video. So the way in which we set the flume up to do swimming trials, we basically make it look like one lap of a pool. So we have a line down the middle. This is a top view, just a sketch. The line down the middle is to make sure the swimmer goes straight. We have some lines at the end, a blue and a red line, to stop the swimmer from hitting the paddle or going into the beach. So we have about 30 metres of swimmable distance in the flume. And from side on, these are those 2 window sections showing you the paddle and the beach. And we're going to look at some video mostly through this set of windows here. So this is what it looks like when there's a swimmer swimming in the flume. In this particular instance, you could just see there, they were swimming in the same direction the waves were propagating. And here they're now swimming against the waves. You can see there's some interesting interaction in a second when the swimmer comes back. You can see they're moving up and down. There's a little bit of heave motion for the swimmer, a little bit of pitch motion. And you can also see, if you look carefully, when they get into the crest of the wave, they tend to speed up, and in the trough, they will slow down. We can start to turn those sort of video observations into data just by using image analysis, I guess. Just this, you can see a red line here that's tracking that swimmer. I'll show that again really quickly. Tracking the swimmer. In this case, it's tracking the midpoint of the bathers. And we can therefore turn their position in the camera into a displacement time history. We've also put accelerometers on the swimmer. I won't talk much about that data today, but if you're interested, happy to talk about it in questions. So I'm going to go through an example of swimming into the waves first. All of the work we've done is just with regular waves to date. And to start things off, to understand how the waves influence swimming, I'm going to start off with that case you just saw where there's swimming in the absence of any waves. And if we do that, we can look at the velocity time history, horizontal velocity of the swimmer, and it looks like this. So even in the absence of waves, a swimmer won't have a constant speed, and that's because the thrust they impart on the fluid is linked to their stroke, which is not continuous, that thrust, and their body also changes orientation and position, so the drag they're experiencing changes as they swim. So there's undulations, and those undulations, we could ignore them and average out and think about just a mean swimming speed. I'll come back to that a bit later in the talk. But to understand the undulations, if we plot on here the stroke, so the stroke here is defined as when the hand enters the water. You can start to see now that most of the undulations in the signal here are linked to stroke behaviour. There's always a little bit of a delay after a stroke before the speed increases, and that's the time taken for the hand to enter the water and then get into the position where the swimmer can actually pull and apply a force on the fluid. There is one undulation there that's a lot bigger than the others, and that undulation is when the swimmer took a breath, so that you can see the effect of that on their swimming. Obviously, the better swimmer you are, the smaller we think these undulations should be. So if we now look at the case where the swimmer is going into a wave, and this particular wave here, I think is a 3-second period wave. You'll see the swimmer come from the left in a second. Here they come, going up and down over the wave. And we can do the same thing and track their position as they swim. And now the displacement time, well, the velocity time history looks like this. We still have undulations at a similar frequency to what we saw with no waves, but we now have something else happening. You can see that there is clearly some frequency content at the wave crest encounter frequency. So obviously when we start looking at those type of time histories, the first thing that we want to do is look at the spectra. So this is the spectra plotted for the case where there's no waves, and you can see that there's a clear peak in the spectrum at the stroke frequency, which is marked there by the vertical dashed line. And then when they're in the presence of waves, we now have a second peak at lower frequency, and that's associated in that case with the crest encounter frequency. So what we can see from this is that there are a couple of dominant frequencies in the velocity time history. And we're going to use that observation a little bit later to come up with a simple model for trying to predict the swimmer's speed. So swimming with the waves, I've got a couple of examples here. The first one, we're going to look at a long period wave that's 4 seconds long. The celerity of this wave is about 3 meters per second. So not even an Olympic world record holder would be able to keep up with that particular wave crest. On the right-hand side, we have a shorter wave that's moving at 1.6 meters per second, and that's about the speed that somebody that is a good swimmer can sprint over 30 meters. Okay, so we're going to start by looking at this 4-second period, and to do this, I've plotted, maybe should transpose that, but I've plotted a position on the vertical axis and time on the horizontal. And the orange lines here are just tracking the wave crest moving through space and time, and then the magenta coloured line is the swimmer. On the bottom figure, we're covering the same time period, but we're just plotting that that forward speed or the horizontal velocity magnitude. And what we're going to do is we can just sort of step through this type of figure. So the blue dashed line now is indicating a particular instance in time, which matches the figure on the right. And what we can see here is the swimmer at this point in time, their head, which we've used to track the swimmer in this case, is slightly ahead of a crest. So you can see that the magenta line is just above the gold line. And as we step through, the crest is now caught up with the swimmer's head, and the crest starts to move ahead because the celerity of the wave is faster than the swimmer can swim. And you see the swimmer start to fall behind like that. So this is a typical result we would see for somebody swimming with the waves. And if I just show you the video, hopefully that's playing over the connection. You can see clearly how they go quite fast when the wave crest is is in the vicinity of them, and as the wave crest moves ahead, they begin to slow down. And you can sort of see that in that top left plot by looking at how the gradient of that magenta line flattens out and then steepens up again either side of the crest. And we see a characteristic increase in the speed as the crest comes past the swimmer. We can also look at the case where it was shorter period waves, and here the swimmer can keep up with those waves. And so if we step through time here, essentially the swimmer is in a fixed position relative to the phase of the wave or relative to the crest location. And so what we can see is very little change in the swimmer speed as they're going in this particular condition. You can just watch the video of them swimming and pretty much keeping up with that crest, falling behind very slightly, but not significantly. Okay, so they're just two examples of swimming in different wave period conditions. Okay, so that's good, and there's some interesting observations, but what can we do to model this? Well, this is the work in progress, but the simplest model that we can do, and what we have done, is we've just assumed that the swimmer is short and compact relative to the wavelength and to the wave. So if we do that, we can just think about the swimmer velocity as being the superposition of two components. One is the velocity associated with the wave as it propagates. So it's the velocity field associated with the propagating wave. And we just have to evaluate that at the location of the swimmer. And then the second term, which is in blue there, is the still water swimming speed of the swimmer. And we just average that. I mentioned that a bit earlier. Just average that for simplicity here. And the plus and minus is accounting for the fact that maybe sometimes we can look at cases where the swimmer is going in the same direction as the wave propagation, as the wave is propagating, and sometimes it's going in the opposite direction. So in this model, the position of the swimmer we can just work out by integrating the velocity over time. And to evaluate the background wave velocity, we can use linear wave theory, or we can extend it to some higher order wave theory if we want to. Here we've just used, I'm going to show you results today just from linear wave theory. We could do more here. We've just evaluated the swimmer by allowing their horizontal position to change, but we've assumed they've stayed at the mean free surface, so at a vertical position of 0. We've played around a bit with that, but in today's talk I'll just present results where we've assumed the swimmer stays at the surface. So these are some example results that come out of that model. The case I'm showing on the left here is where the swimmer is going at 1.3 meters per second in a 3-second period wave. And the plus means they're going in the same direction as the waves. And you can see that behavior is a bit similar to what we just saw in the experiments. One thing you can see is we get this steepening of the red line around the wave crest. And what that means is that the average forward speed of the swimmer is now larger than their still water swimming speed, so 1.37 meters per second instead of 1.3 meters per second. And the physical explanation here is that when they're in the crest of the wave, they're going faster and they can keep up with that crest of the wave for slightly longer than what they're held in a trough. So that sort of nonlinear behavior gives them a slightly faster average speed. And when they're swimming against the waves, it's sort of the opposite. So here we're moving backwards relative to the wave propagation. And you sort of get the opposite effect happening. The relative velocity now is different in the crest and the trough, such that you spend more time being slowed down than sped up as the wave propagates past you. So your average speed here is minus 1.26 relative to 1.3, which was your still water swimming speed. So we can compare this model with the experiments, and the top right there is if you just plot the velocity time history predicted from that simple model against the measured velocity time history I showed you earlier. They're somewhat similar, but what we're actually interested in terms of comparison is what is happening to the average speed at which the swimmer is moving. So on the left here, I've got a plot from the experiments. The different colours here are different swimmers. The horizontal axis is the wave period, and we've held the wave height and the water depth constant in all of these cases. So what you can see in the experiments is there's clearly an effect. So as we change the wave period, as we reduce the wave period, we're actually increasing the maximum horizontal velocity at the surface associated with the wave. And that's having an influence on the swimmer. And you can see here that the average speed of the swimmer is reducing as we reduce the wave period. Our simple model has the same trend, but the trend is less significant. So on the left-hand side, we sort of see as we move from 4 to 2 second period, we're getting a reduction in 10% for the red swimmer. And the red swimmer here is the faster, more elite swimmer. And we're seeing a drop of 23% for the less experienced swimmer. And we see in the theoretical model, those differences are not as big, but the trend is similar. So what are we missing? Well, the simple model here is just superimposing the still water speed onto the background wave velocity. And that's ignoring the fact that the waves could have a change or could influence the swimmer's behaviour. And if we just look at these two still shots quickly, on the left we've got still water, and what I want to draw your attention to is the width at which those the feet of the swimmer are apart during their kick here. On the left is in still water, and the feet are actually quite close together, which will clearly reduce the frontal area of the swimmer and reduce the drag. On the right, the same swimmer is in the crest of a wave. You can see how that's clearly altered his technique. His legs are much further apart, and potentially, therefore, he's seeing a lot more drag, and that might be one reason why we see much larger decreases in velocity than we might predict with our model. Okay. And lastly, we can also just compare similar conditions for going with the waves. And you can see sort of similar results here. But if you look on the bottom two plots, again, the model is not predicting as much of a change in velocity as we see in our observations. So again, there's some behavioural change, and in this particular case, there may even be a little bit of planing or surfing that's not captured by our simple model. That's happening in the actual experiments. That's all I wanted to talk about. So we've got qualitative agreement between a simple model and experiments, and that somewhat explains why you swim faster with rather than into waves, and waves will affect slower swimmers proportionally more. But there is other things happening, so some interesting interactions that are influencing the behaviour of the swimmer. So yeah, thank you very much for your attention.
Yeah, thanks, Scott. Very interesting